The first talk is by Yongsoo. He's going to join us again on stage, and he's going to talk about advances on homomorphic encryption for multiple parties.
Good afternoon, everyone. It's me again, who gave a boring algorithmic lecture in the morning. But this one is quite different. This is more like a survey on recent papers on homomorphic encryption for multiple parties, which will be very likely to be used in the future in various applications, I suppose. So, okay. As you know, we can classify these use cases of homomorphic encryption generally in two scenarios. The first one is a 2PC, where the client holds the data and secret key, and the computation is taken place on the cloud, and the client finally receives an encrypted result and decrypt it. So far, so good. So this privacy-preserving personalized service can be easily implemented with the standard single key homomorphic encryption. It's good. But however, some more promising and interesting applications are over this in this scenario 2, where there are more than 2 data owners who'd like to jointly compute something by aggregating data and analyze them. So in this case, the key management problem arises because, of course, it would be great if there's a trust third party, but there's no trust third party arrays. So we need for some alternative solution that is homomorphic variant of homomorphic encryption for multiple parties with a distributed authority. And if you have such a nice primitive, then you can, it is almost straightforward to build a multi-party protocol from such a homomorphic encryption primitive. You can simply generate key, encrypt data, and evaluate some circuit, and finally decrypt it. And this decryption can be done in a distributed manner. And compared to the usual, the usual MPC techniques such as garbage circuit or secret sharing, this protocol enjoys a better communication cost, and round complexity can be minimized, and all computation will be done on the server. So this is much more user-friendly, while it suffers from higher computational complexity on the cloud. So there's a trade-off between these two features. So now I'm gonna introduce two primary directions on this homomorphic encryption for multiple parties. So the first one is called threshold HE. So in this threshold HE, there are n parties who are going to generate a joint public key PK. Or a trusted third party comes in and generate everything and go away, or they can generate public key by themselves in a distributed manner. And at the end of this key generation protocol, everyone obtains a joint public key, and each party obtains some share of a secret key S. So here, as illustrated here, everyone obtains this PK, and this shared secret key theoretically exists, but each party obtains some share of this secret key. And for encryption and evaluation, this common public key is used. And in decryption, depending on how we generated this shared public key, we can T out of n, T shares out of these n shares can be used to recover the secret key or decrypt a ciphertext in a distributed manner. So in this case, this protocol is secure as long as an adversary against an adversary colluding at most T-1 parties here. Okay, so another direction is called multi-key homomorphic encryption, or shortly MKHE. the primary difference between multi-key HE and thorough HE is that key generation is not a protocol, but this is a key generation algorithm performed by each party PI totally independently. So in this scenario, each party PI generates his or her own key pair, like this guy generates this yellow public key and yellow secret key and blue one and orange one and so on. And in the case of encryption, you can just use one public key and output is a single key ciphertext. But in the case of evaluation, you can actually evaluate on ciphertext under possibly different set of keys. So fresh ciphertext are single key ciphertext, but if you add two ciphertexts under different keys, then the output is a two key ciphertext. And in the case of a decryption, the decryption requires all secret keys involved in this computation of the output ciphertext. And again, distributed decryption is possible. So if I compare these two approaches more generally, threshold homomorphic encryption enjoys better efficiency in evaluation because its key generation protocol can be a little bit complicated, but once this key setup is done, then encryption and homomorphic evaluation is almost the same as a single key case. So its computation is efficient, but however, its key structure is static and the key generation is usually interactive. So in this case, this participant, a set of parties should be determined at the beginning and cannot be changed later, meaning that a new party cannot join the computation later, so just fixed. While in this multi-key setup, this is much more flexible and dynamic because each party can generate its own key pair and use this key to encrypt this message, and anyone can join the computation at any time. So this is much more flexible, but it suffers from like a relatively poor performance that this ciphertext is larger than single key ciphertext and the homomorphic operation is more expensive depending on the number of keys in this computation. So there's pros and cons. Okay, so this is a large research landscape. Let me first focus on this threshold homomorphic encryption. So I can classify this threshold homomorphic encryption into two cases where t is less than t or t is exactly equal to n. So the case where t equals n is called multi-party homomorphic encryption also. And in this line of work where t is strictly smaller than p, smaller than n, there are very limited, only a few publications in this line of work. So there was one theoretic paper in Crypto 18 that's a great paper, but it kind of requires a huge parameter. And there was a recent paper about much more efficient threshold homomorphic encryption key generation, but it requires relatively stronger assumption in distributed decryption. So definitely we need much more focus and research on this line of work. While this multi-party homomorphic encryption case is relatively well studied, so this primitive was first introduced about more than 10 years ago. And there are some recent papers which improved this performance of this old scheme. So now we know how to design multi-party BGP or multi-party FFV schemes. And this scheme is also implemented in the Letigo library. But still, it requires some interactive key generation between these n parties in the computation. And so I'm gonna today I'm gonna briefly introduce 5 papers of mine, and this is the first one. So in 2021, I somehow was able to combine these two primitive, multi-key homomorphic encryption and multi-party homomorphic encryption. So now I'm I call this primitive the multi-group homomorphic encryption, which is a generalized notion of both MPHE and MKHE. So meaning that these two primitives are a specific case of this multi-group HE, and which enjoys the best of two worlds, basically. And I also propose the non-interactive key generation algorithm where each party doesn't have to know about any information about other parties, but just generate its own key, and the joint key, public key, can be built by simply collecting these individually generated public keys. There's a poster about this paper, so please check out our poster, and my student will answer any of your questions. He's there. And in another line of work on multi-key homomorphic encryption, the first paper was published in 2012, and after that there has been a series of works like designing, for example, mostly multi-key variants of a GSW scheme, or there are some other multi-key schemes from LWE, but all studies until 2017 were mostly theoretic, and there were no known implementation results. So after that, I basically did two lines of follow-up researches. One is on TFHE, and another one is on CKKS and FV. So in these two papers, in 2019, I designed the first multi-key homomorphic encryption scheme with the implementation from the TFHE scheme. And in this paper, to support multi-key variants of a blind rotation process, I designed what's called a hybrid product, which is some operation between multi-key ring LWE ciphertext and the single key GSW ciphertext. But this GSW ciphertext is not the usual GSW, but has some certain structure to support this hybrid operation. And recently, it must be 23, but recently we wrote another paper which improves the previous paper, and we achieved the quasi-linear complexity. So I believe this is almost optimal now, and we also prepared another poster explaining this scheme, so please find my another student for any other questions on this paper. And today I'll be more focusing on this line of work, multi-key CKKS and multi-key FV. In 2019, I wrote a paper about multi-key CKKS, which providing a new functionality of a multi-key linearization with a quadratic complexity. And more recently, I improved this scheme by and achieved almost optimal linear complexity also. So I will explain more about these two papers today. Okay, so let me first give a very quick overview about the CDK19 scheme. So in this paper, so this is a multi-key CKKS. So encryption is just the same as the usual CKKS. So a fresh ciphertext is just a pair of polynomial such that C0 plus C1s is approximately equal to the message M modulo Q. But when you add two ciphertext, this format can change. So for example, suppose that we are given two ciphertexts C and C prime where, over M and M prime, where the first ciphertext is under secret S and the second ciphertext is under another secret key S prime. Then their summation is defined by this triple of a polynomial that C0 plus C0 prime, comma C1 prime. And this ciphertext can be decrypted by two keys, S and S prime, by computing this value, like Just you can take an inner product between this ciphertext and one S prime. So the result is it is easy to check that the result is approximately equal to n plus n prime modulo q. So this is why the size of a multi-key ciphertext may increase during the computation. When this ciphertext under different keys meets, then we have a larger ciphertext. So still, homomorphic addition is simple, but the multiplication is more challenging. So in general, on multi-key CKK ciphertext is the form of this n plus 1 to probe polynomials, where n denotes the number of parties associated with this ciphertext, and it has a decryption structure like this. So S1 to Sn are secret keys of parties, party 1 to party n, who are like involved with this ciphertext. So just a more general form of this case. Okay, so we are, yeah, the more technical part is coming. So, so the intuition is similar to just a usual CKKS multiplication. So I will just for simplicity that we are given two ciphertexts under n keys, the same set of keys. So they are both n plus 1 to probe polynomials. If they are encrypted under different keys, then you can simply pad zeros to make them have the same key. So we first compute the simple product as usual. So you have this tensor product Cij, where Cij is a product of Ci and Cj prime. And actually this ciphertext is encryption of M prime, where under the secret key S tensor S. So you need these values, Si times Sj, to decrypt this component C sub I, J. This is just the same as CKKS, but the multi-key variant. So the problem is the following. We need to linearize this ciphertext to obtain this canonical form, original form. But the thing is that we actually need a key switching key for this key component Si times Sj. But the problem is that Si is a secret key of party I, while Sj is a secret key of party J. So there's no party who can generate some key switching key for this product of Si and Sj. So we somehow modify the key generation algorithm of CKKS so that now this public key has a more complicated form, but somehow you can combine public keys of party I, party J to linearize this component Ci, J. So this I didn't even define what those terms are, but these blue ones are some components of public key of the J's party, while these red vectors are some components of the public key of party I. So you, as you can see, you perform some external product that I explained this morning, and then obtain some triple of polynomial, which is actually encryption of C sub I, J times Si Sj, but this is now encrypted under one Si Sj. So it has been linearized. So for those who want to see more details, this is why I didn't show you how the key generation protocol. So we have a very complicated key generation protocol of generating some like a second secret key and have some common random string and many vectors B, D, U, and V. They are just components of a public key. So I'm gonna skip the details, but just remember that we can somehow combine the public keys of party I and party J to linearize this component corresponding to Si times Sj. So obviously it requires a quadratic complexity with the number of parties n. The reason is that there are n square many components here in the tensor product. So that was what we could achieve in 2019. And in fact, I thought back then in 2019, I thought we already achieved a kind of optimal complexity because this is just the same pipeline as the usual CKKS, but this tensor product already has a quadratically many entries. So maybe this is the best we can achieve, but it turns out I was wrong. And here's some motivation. So if there is a way to reduce the complexity, then we probably need to use this multiplicative structure, because if Cij are just independent variables, then there's nothing you can do, but this quadratic complexity is inevitable. But probably there is a possibility to use this multiplicative property. So if you manipulate this equation very well, then you can write down the final output of this linearization process as a tuple of polynomials C0 to Cn. Oh, stars are missing here. So C0 is here and Ck star is here. So you can find just a closed formula where you can see that there are some bunch of terms related to Cij, so here and there. So the question is, can you linearize this term directly? Can you compute this term directly from Ci and Cj prime, even without computing this term Cij? So actually, it seems to be infeasible, since this computation involves Gaussian decomposition. So this is an external product. So we first need to compute this decomposition of Ci, j, and then take an inner product with Bj. So, but this Gaussian decomposition is not a homomorphism mathematically. So probably there's no way to take advantage from this multiplicative property. So this is where our new idea, the new notion of a homomorphic Gaussian decomposition comes in. So here we propose a new notion of Gaussian decomposition where you can perform some operation between decompositions, vectors, I mean. So the first observation is that actually the real primary goal of Gaussian decomposition is not to find a very specific vector, but it suffices to find the short vector in the inverse image of this inner product function. So it is okay to find an arbitrarily short, not arbitrarily, but sufficiently short vector in this inverse image. So the definition of a homomorphic Gaussian decomposition is following. I say that Gaussian decomposition is homomorphic if you can actually perform computation between these decompositions of A and B to obtain another vector which can be viewed as a valid decomposition of A plus B or A times B. So this is kind of similar to the definition of a homomorphic encryption. You can perform some operation over decomposed vectors. And it's very amazing fact that this RNS-based decomposition that we are using every year has this homomorphic property. You can simply check this CRT theorem that this decomposition and this decomposition, then their product is congruent to A times B modulo Qi, so you can easily prove this property of a homomorphic Gaussian decomposition. So now, if Gaussian decomposition H is homomorphic, instead of computing this decomposition of Ci, j, we replace this term by this product of a decomposition of Ci and decomposition of Cj prime. And these decompositions of Ci and decompositions of Cj prime, they can be pre-computed and reused. Once we have these all decompositions, this term was one of the terms in this closed formula in the final ciphertext. And this formula can be rewritten in this way. And this is equal to this one. And you can see that this summation, this term now came out of this sigma. So this term can be pre-computed independently from the index k. And the same happens, or similar can be done for another term. So if you assume that this is a homomorphic, then you can actually modify the linearization algorithm to obtain linear complexity. So to sum up, we achieve a linear complexity. I believe this is now really asymptotically optimal. And actually, it is not straightforward to apply this idea to BFV because BFV has a kind of unnatural tensor product operation, but still we found a way to apply a similar idea. But still, multi-key VFV is linear but slightly smaller than CKCS. And this new multiplication also introduced a larger error compared to the previous one, but there is an easy fix. You can just use a larger special modulus. That's it. So conclusion. So we have a lot of tools: threshold HE, multiparty HE, Multikey HE, MGHE. Techniques has been developed very significantly, and of course, the need is accurate. We definitely need these techniques in many applications, and they have been fast enough to be used in practice, I believe. So I think it is really time to put these tools bring to practice. Yeah, that's it, and thank you for your attention.
Any questions?
I've got a comment, and because I'm now in Belgium, I have to pretend to be Ivo Desmet with my comments for the old people in the audience. If you go to slide 7.
Oh, very specific.
No, just because I remembered it. I think it was 7. No. So, no, so it must have been earlier. Sorry.
Earlier, you mean?
No, there's something about you had timeline. Maybe it was slide 8 then. Yeah, here we go. Right, yes. So T is less than N. If you actually go back to AsiaCrypt 2013, there's a paper there which does T is less than N over 3 and robust threshold FHE in that paper. And also, if you go to the previous slide, slide 8, you're static and interactive on threshold HE. You can make it non-static by having a protocol to do the resharing. So, and it's a relatively simple protocol, so it's it's not really static. It's kind of the resharing is about as hard as a distributed decryption anyway. So that's it's much easier than your kind of slides make clear.
Oh, yeah, thank you for a great comment. I wasn't aware of those researches, so yeah, I will definitely read their papers.
Okay. Any other questions?
So yes, I have a question about the relinearization itself. So it's true that very often we say that for example to multiply ciphertext we have to have an encryption of S square. So here this S square becomes SI SJ, which is a problem because no party has both SI and SJ. But when we formalize it in Chimera, we changed the approach and used, for example, the pre-computed multiplication by S, which so it's one GSW ciphertext that allows to evaluate any polynomials in S. Could we apply this approach to this? Because in this case, there would not be cross-term, but just multiplication by SI and multiplication by SJ.
But can you support multiplication between encryption of SI and SJ encrypted under SI and SJ?
So probably yes, if you have a public key, ring LWE public key.
So actually that type of operations were studied in Multikey GSW scheme. So actually, so this, I didn't explain details here, but there is another like a variant of this linearization algorithm where we can kind of do more pre-computation on public keys of PI and PJ to pre-compute the linearization key for SI times SJ. That's possible, but overall, that's usually more less efficient because we need like n square many linearization keys there. So yeah, but that approach was also described in this CDK19 paper.
Okay, yeah. Thanks.
Thank you.
Okay.
Thank you very much.
Let's thank Yongsoo again.